Welcome everyone. I'm here with you at Consteel Meetup conference. My name is Regina Szakál. I am a civil engineer, fire protection engineer, and commercial director representing MCR Dunamenti. My task today is to briefly present to you the basis and the results of the collaboration we have carried out with the developers at Consteel. So, namely the determination of the required thickness of intumescent fire protection coating. I've broken today's topic down into three main points. As a first step, I will introduce the key concept that influence the fire protection solutions of steel structures and the determination of layer thicknesses of the intumescent fire protection coating. Next, I will explain factors have the greatest impact on a project's cost effectiveness from the perspective of structural fire protection. Then I will outline the critical aspects of design from the perspective of structural fire protection that may limit feasibility during the construction phase. Let's see the basic factors of fire protection of steel structures. These are based in the Eurocode's fire protection concept. This is section factor and critical temperature. The section factor indicates how well a steel member resists heating due to its geometry and massiveness. This value expressed as a ratio which divides the perimeter of the section exposed to fire by the cross-sectional area that heats up. The higher the value of this ratio, the thinner the section's walls, and the greater the thermal insulation required to prevent heating. So this will be a key aspect of cost-effective fire protection solution. The critical temperature is determined by a mechanical fire analysis, which specifies the maximum temperature to which a structural element can be heated up without losing its load-bearing capacity. The higher the critical temperature of the structural element, the thinner the additional thermal insulation layer required in the event of a fire. The next factor is the cross-sectional shape, which is defined in the testing standard, and at first glance this may not seem like a significant factor, shape, whatever, the shape of the factor. But due to the heat-activated intumescent mechanism of the fire retardant paint, it becomes a key element. Imagine the working mechanism that around 200 Celsius degrees, a carbon-based foam formation begins, resulting in expansion ratio which is 50 times of the original dry thickness, and it shows on the picture on the slide. On an open section such as an I-beam, this process occurs without any issue. The foam expands parallel to the flanges and surrounds the section. However, with hollow sections, particularly the circular ones, this effect can cause a lot of problems. Since the paint particles originating from the original diameter of the circle must cover a larger diameter as a result of the foaming. Imagine that, and also you can look at that little drawing. So the foam can crack up during one phase of the foaming process. To ensure that the surface is filled in during reforming after the crack, a much thicker coating layer is required on circular cross-sections. It causes higher dry layer thicknesses for the circular hollow sections in any kind of solutions and any kind of products. The test standard distinguishes between 3-sided and 4-sided fire exposure. A beam is considered 3-sided if it's supported by a reinforced concrete slab, whereas a freestanding column, for example, is considered 4-sided. The environmental use categories based on EAD regulations also influences the fire protection solution, as the intumescent coating must also protect it against these environmental factors. The type of coating system required as primer, fire protection coating and top coat. is determined by the environmental factors. So these are the factors mentioned that determine the composition of a fire protection coating system, including its types and thicknesses. Shows an example of a technical evaluation. ETA means European Technical Assessment. This is for a fire protection coating. It is a table used to the determination of the required coating thickness based on the section factor, the critical temperature, the shape of the section, and the fire performance requirement. I would like to highlight a trend that is clearly visible in the values in the table's columns. So pick a column with your eyes, or which is indicated already by me, and follow the numbers, and you can discover this trend with me. The higher the section factor, so the thinner a structural element is, the greater, the thicker fire protection layer is required. Another trend, which I mentioned earlier, but which is also clearly illustrated in this table, is the higher the critical temperature to which the structure can heat up, the thinner the layer of the fire protection paint needed to protect it. Therefore, the structural engineer plays a key role in cost effectiveness, as the critical temperature has a significant impact on the fire protection costs. So here we are. I would also like to draw your attention to another factor, which can be seen in the lower left section of the table. When higher the fire-resistant performance is required, the performance of paints becomes increasingly limited. So it may happen that for a section with a high section factor, so for a slender section, there will be no validated solution for the given product at low critical temperatures. Of course, this varies by product, but the trend is the same for all of them. So we need to pay attention for this effect. Based on what you've heard in the past few minutes, I will summarize the limitations involved in determination of fire protection layer thicknesses. When dealing with high fire resistance requirement, special attention must be paid to the section factor and the critical temperature of the structural member. However, the good news is if we need to change a structural element and choose a more massive one because of fire protection reasons, under the same applied loads and effects, the section factor is reduced, means we have an element with higher massivity, and its critical temperature will also increase, since it will have a higher utilization rate reserve. So it will solve our problem easily. An important limitation, solutions and layer thicknesses certified by the test standard do not apply to cross-sections exceeding 400 section factor. Particular attention must be paid to this when designing primary structural elements which has a fire performance requirement. The final major limiting factor is the environmental exposure category, which has already been mentioned and which may exclude the use of certain product types. For example, in generally saying, a water-based fire retardant paint can be generally used up to corrosion category C3, solvent-based paints up to C4, and in category C5 only high resistance two-component epoxy coatings are suitable. But these values are based on their own ETAs and durability tests, so this is just a general idea for you to see how limited it can be. As my studies and later my engineering and professional experience became interlinked with the commercial side of the business, it became increasingly clear that designers needed assistance to carry out their design task with greater confidence in the field of structural fire protection. In order to minimize serious obstacles or even unfeasible situations during the construction phase, So, in my opinion, it was a very effective and forward-thinking idea to implement this into the Consteel software, which is used for steel structure design. This way, users, engineers not only receive data from the software, but also results that confirm that to them that the design structure can be integrated into the fire protection concept and that the entire project is feasible. Thank you for your kind attention. This was my presentation shortly. I hope I have highlighted some useful insights for you that will help your work. Best luck and keep up the good work, everyone. Thank you. Bye.